It has been over 50 years since a human viewed the lunar surface from a spacecraft window. While the Apollo missions proved it was possible, the digital flight computers and composite materials used today are different from the analog systems of the 1960s. Artemis II serves as a live validation of Orion's life support and deep space navigation. Since this mission does not involve a landing, NASA's priority is measuring how these integrated systems protect a crew while exposed to the radiation and vacuum of the lunar environment. The flight path mirrors Apollo 8, a high-stakes verification flight where the crew relies on hardware that has never been tested with humans in deep space. Success here provides the data required to clear the next mission for a landing on the lunar South Pole. Moving from hardware to the crew, astronauts spend months refining their physical responses to weightlessness and confined quarters long before launch. Training inside a 6.2 million-gallon pool allows the crew to practice technical tasks in a simulated microgravity environment, focusing on emergency egress and hatch operations. The crew also undergoes psychological screening to prepare for the isolation of a journey, where the distance from Earth makes an immediate return impossible if a problem develops. Developing these procedures on the ground ensures the crew can maintain the spacecraft during the transit phase of the mission. The mission begins with the SLS rocket generating 8.8 million pounds of thrust to lift the Orion capsule into orbit. Once in high Earth orbit, the crew enters a parking phase to verify that electrical and communication arrays are functioning. After verification, they initiate the translunar injection, or TLI. This engine burn provides the velocity to escape Earth's orbit and reach the Moon. The TLI burn requires the engine to fire at a specific vector for a precise duration. If the engine shuts down early, the capsule will fail to enter the lunar trajectory. Successfully completing this maneuver marks the transition into the 3-day transit across the void between the Earth and the Moon. Following the injection burn, the capsule enters a coasting phase, where the crew manages the daily operations of the spacecraft. The daily schedule is divided into blocks for systems maintenance, 2 hours of cardiovascular exercise to prevent bone density loss, and public broadcasts. As the capsule reaches the Moon, it utilizes lunar gravity to perform a flyby maneuver. The spacecraft will pass behind the far side, briefly losing contact with ground control. During this blackout, the crew will observe the lunar horizon while the Earth is entirely obscured from view. Completing this flyby proves that the capsule's life support and shielding can sustain human life during a multi-day deep space transit. The final phase of the mission is the return to Earth, which represents the most difficult technical hurdle. The capsule hits the upper atmosphere at Mach 32. This compression of air generates temperatures reaching 5,000 degrees Fahrenheit, approximately half as hot as the surface of the Sun. To manage this heat, Orion uses an ablative shield made of blocks that are designed to erode during descent. As these tiles burn away, they carry the thermal energy away from the crew module. To further reduce thermal stress, Orion performs a skip re-entry. The capsule dips into the atmosphere to slow down, then bounces back into the vacuum of space to cool before its final descent. This maneuver lowers the G-forces experienced by the astronauts and allows for a more precise landing at the splashdown site. The mission ends with a parachute-assisted splashdown in the Pacific Ocean, where recovery teams await the crew. A successful recovery of the Artemis II crew validates the architecture required for Artemis III to place humans back on the lunar surface.